Recording. There we go. So, welcome to today's introduction to quantum computing lecture. So I'm very glad that today I'm not going to be talking here too much, but Professor Pauli Miettinen is going to talk about some of the I would say complexity of quantum computing and maybe classical computing. And well, we've been talking about complex numbers and so on already in the course, but this is a different topic and relates to the I suppose to the what can be and what cannot be done with the quantum computers. And as far as I know, we still cannot have a black magic to solve impossible problems, even where everyone is excited about quantum computing and so on. But I will not do any more spoilers. So Pauli, please go ahead anytime you are ready.
Thank you, Tommy. So I will start with a question regarding the organization. Do you typically give this in a one go or have a break in between?
I think we more often than not we've continued without a break. But I have a quiz here actually. So if you we can do a poll in the midway if we want to have a break. So
you can do that. That would be great. Let me see if I come up with the great ideas of quizzes, I might ask you, Tommy, to just do them like on the fly, or maybe if we have a break, I can ask you to make a couple of quizzes during the break. But yeah, without further ado, welcome from my part. I was in the first lecture, so hopefully you might still remember Professor Pauli Miettinen. I'm a professor of data science. My background is in a bit more in algorithms and complexity theory. And so today I'm going to tell you what we cannot do with the computers we don't have, aka the quantum computers. So start, what's this all about? So if you are a computer scientist on background, I understand that we have computer scientists, maybe some mathematicians and physicists, so on. But computer scientists might know already computational complexity, which is the field of computer science that studies the hardness of solving computational problems. So in other words, lower bounds of how fast the computational resources, the needed computational resources increase as the input size grows. This is in contrast to algorithms research, which is more familiar, I would say, to at least for all computer scientists should be somewhat familiar with algorithms research from like data structures and algorithm scores and so on. And in algorithms research, we study the upper bounds. So what is the maximum of resources we will need to solve some problem? That's when we get those that you can do sorting in big O n log n time, for example. And then there is the computability research, which is asking the bigger question of what is actually doable with computers at all. So not how efficiently it is doable, but what is doable at all. And computability research is somewhere in between computer science and mathematics. But I would argue that the computational complexity and algorithms research are more strongly in computer scientists' field. Obviously, also some mathematicians do study this, especially computational complexity. Now, computability research, well, it's can be somewhat easily motivated on a very important mathematical question, what we actually can do with the computers. So those of you who know the famous halving problem, that no computer can solve the halving problem, that's an example of computability research. Those of you who don't know halving problem, that's the problem asking that given a source code of a program, will this program halve or will it end up in an infinite loop? That's an example of a program that you cannot compute no matter how much time you're given. Algorithms research is easy to motivate. I mean, that's kind of like what a significant portion of computer science is. So really, what is the most efficient way to compute this? What is the most efficient way to compute that? But then there's still the question of why on earth would anybody be interested in studying the computational complexity? So why study what we cannot do? So it seems like like a pessimist's hobby, something kind of like rather miserable job to do. But why would we do? Well, for example, studying lower bounds save us from spending time on trying to do things we cannot or think we cannot do. So if we know that this thing cannot be solved faster than some effort, then there's not much point on trying to find an algorithm that actually can do it better. That's a traditional motivation for computational complexity study. But in addition, they actually are constructively useful. So they actually can be utilized to allow things. And actually, right now, we are utilizing computational complexity. This connection is encrypted. And the encryption needs, essentially, you use public key cryptography to share the private keys, the eventual keys. But initially, you need the public key cryptography, and public key cryptography is a prime example of something where we assume that computing certain things is hard, and hence if we require computing those things in order to break the cryptography cannot be break efficiently because computing is hard. That is also something that you might already know. The quantum computers might change somehow. I'll get to that later. But in addition, lower bounds do tell us about problems we want to solve. So it's sometimes you can build the connections between different kind of, or you can build lots of what we're going to do is to build connections between problems that are seemingly completely unrelated. But seen from the computational complexities point of view, they actually turn out to be equivalent. So building these kind of connections is what I at least personally think is one of the most interesting part of computational complexity. And if I just have time, I hope I have some time, I'll get into telling how we might actually be able to understand a little bit about the world we live in if we understand computational complexity. So I got this briefly, but just to give you the basic idea. So if you want to do a proper complexity research, you have to start with some kind of model of computation. So if you want to argue that that computer cannot solve this problem using less than this much time, you have to have some model of what does a computer mean, so that you can do your proofs using that model. And classically, we've been using Turing machines. Those of you who have taken some courses in computer science might know Turing machines. That's the thing there on the right. Let me see if no, that's not the thing. Just a second. I'm seeing if I can have a convenient way of showing something. No, it doesn't really see. Okay, whatever. Okay, so we have the Turing machines, or nowadays we might do this with random access machines. So random access machine is a abstract thingy which can access memory in a constant time. It has some memory. Lots of the proofs use Boolean circuits, something like there on the right at the below. So this kind of things that you could, in principle, just solder yourself on a circuit board. And in practice, well, computers do look something like that, although infinitely more complicated, to be honest. But for this course, for today's lecture, just think of any computer that has unlimited memory. So today we're not going to go through any detail proof, so it doesn't really matter what's the the model of our computation. You might just think, if I talk about these things, you just think of a computer, like a classical computer, with the caveat that we assume that it has unlimited memory. That's a quite standard assumption. So then when we have our model of computation, we can say something about the efficiency of the computation. So now we just think of standard computer. So as I said, what we typically do, we measure the complexity as a function of the size of the input. And standardly, we denote the size of the input by n. So almost everywhere here, you see a small letter n denoting the size of the input. What exactly is the input? It depends on the problem. Typically, we don't care. So you could go down with, when we talk about computers, you could always just count the number of bits. That would be the input. But typically, you don't really bother as long as the whatever you use as the size of the input is nicely related to the eventual size of the number of the bits you need. So typically we talk about just the number of the values or size of the matrix or something like that as the size of the input, and then agree that okay, but we won't need more than a polynomially many more bits to actually encode this for a computer, and as long as it's only polynomial, then it doesn't matter, and I'll come to that why it doesn't matter in a second. And then there's typically two kinds of complexities we are studying. So we study time complexity and space complexity. So time complexity is the number of elementary steps our computer needs to do in order to solve the problem of size n as a function of this n. All of you who've seen this sorting algorithm can be done in big O n log n. That's exactly what we talk about when we talk about time complexity. So we make n times logarithm of n steps, elementary steps, plus some constants. Space complexity is less commonly studied, but it's equally important, which is the number of memory locations we need as a function of n. So how much memory we actually need in order to solve the problem. For some problems we need, we can, or oftentimes we can change these. So we might win some time by using more space, and vice versa. We might save some space by using more time. Dynamic programming, where you basically store intermediate solutions on a table, is a prime example of how you change some space. You use more space in order to make the algorithm a bit faster. But then before we can go talking about what we cannot do, so basically what is inefficient, we need to say what is efficient. And in computational complexity, typically we say that the computation is efficient if it has a time complexity or space complexity which is polynomial in the size of the input. So in other words, the computer takes at most a times n to the power of b plus c steps for some constants a, b, and c that are independent of the size of the input. And then we say that it's a polynomial time, or it takes at most polynomial number of locations. We say it's a polynomial space. Polynomial space might not be efficient space-wise, however, or it kind of like is, but it's completely different beasts. We'll get to that towards the end of the lecture. What's the difference between polynomial time and polynomial space? So that's the definition of efficient. So from now on, when I say that, okay, we can do this efficiently or we cannot do this efficiently, what I mean is we can do this with number of elementary steps, which is polynomial on the input size, or we cannot, or we don't know whether we can do it with polynomial number of steps. Now you might wonder why polynomial? Because as I said, there's no bound. It's any polynomial will do. So there's no bound on what is the degree of the polynomial. So we might have an algorithm that takes like 10n to the power of 10 million steps. And based on what I just said on the previous slide, I would still call it efficient algorithm. Well, obviously it ain't efficient algorithm. I mean, n to the power of 10 million is not efficient. As soon as my n is more than 1, I'm kind of like busted there. This, however, is something that in practice never seems to happen. So almost all problems that we can solve in polynomial time, we can solve with a polynomial in time, which is polynomial with some relatively small degree. So for example, approximately 4, n to the power of 4. So in reality, our exponents don't seem to be big. That's the first rationale why we don't actually worry about n to the power of 10 million. It's in principle possible that we'll have an algorithm which takes n to the power of 10 million steps. But in practice, it seems that if we have an algorithm which takes n to the power of 10 million, we can also make another algorithm which takes n to the power of 4 or so. However, I have to point out that even though the exponents in the n is typically not very big, the hidden constants, so the constant there in our polynomial can be quite big. So the constants hidden with the big O notation, which I hope is familiar for most of you or all of you. And that can sometimes be pretty horrible. Like it can very well be it's to the power of 10,000 times n to the power of 1.37, which like that would be big O n to the power of 1.37 would look quite fast, but then you have an absolutely ridiculous hidden constant somewhere there. But that doesn't change the fact that we still think polynomials are effective. But there is more fundamental reason why we like to use polynomials. And that's because polynomials are closed under typical operations. So if I have two polynomials and I sum them up, that still is a polynomial. I multiply them together, that still is a polynomial. And if I take the composition of them, it still is a polynomial. And this is the reason why we worry, like why we say polynomials, why we work with polynomials. So I just said that for the input size, we don't really care if we count the number of bits to store, or maybe we talk about a matrix and we just say it's the size of the matrix. We don't care because we know that the size of the matrix and the number of bits it takes to actually store the matrix are somehow polynomially related to each other, and hence our time complexity will just grow by some polynomial. And if we do have some other polynomial there, then we're still within a polynomial. It's still some other polynomial. And as long as we just care about that, we say that efficiency, as we say in the computational complexity theory, efficiency is just any polynomial is efficient, then it doesn't really matter too much which polynomial it is there. And so we can kind of like brush lots of nasty details under the rug by saying that, oh, but that will only have a polynomial effect on the running time. Furthermore, if we want to show that some stuff is inefficient, like truly inefficient, then obviously this claim, which is like what the computational complexity is all about, then obviously this claim is stronger if our efficient computation model actually includes what we would consider practically inefficient cases. So if we say that we cannot solve this with efficient methods, but our efficient methods actually contain also practically horribly inefficient methods, then we are making a stronger claim than if our claim would be something like that we can solve this with algorithm that takes exactly 7 times n times log of n steps or something like that. So actually working with polynomials from the complexity theory point of view is just makes everything more stronger. But now you have to I have to point out that in algorithms research, so not in the complexity research, but in algorithms research, we actually are commonly very interested about what polynomial we're talking about. We're not interested about hiding the polynomial factors somewhere. We're actually very, very keenly interested on questions like, does our algorithm take n squared or n log n time? Because that can be the difference between infeasible in practice or perfectly doable in practice. Like n squared over big data is absolutely undoable, n log n is easily doable. So, but that's algorithms research. What we're talking today is computational complexity. And here we just consider n squared and n log n. It's all the same, like essentially polynomial time. So This brings us to our first big claim of today, the so-called Church-Turing thesis. This might be familiar to some of you, but I actually hope it is familiar to some of you. But if you haven't heard it, it goes as follows. It says that every physically realizable computation device can be simulated by a Turing machine. It's not a theorem. There are no proofs. It's kind of like very hard to make a proof about something we don't have and can't even imagine. But generally, we do expect this to be true. So what it says basically is that whatever model of computation can physically be realized, so whatever kind of computers we will ever have in the future, be they quantum computers, be they soap bubble computers, don't love this is proper, like some people have actually proposed to use soap bubbles for solving problems. Can be DNA computation based on the idea that folding DNA is supposedly solving hard problems. So maybe we can encode our problems in a DNA and then let it fold and use that for solving whatever. The Church-Turing thesis says that we can model or we can simulate that computation using a Turing machine. And by proxy, then using essentially, we can do the simulation using our standard computers with some caveats for the physical resources, like we might run out of space or something. But in principle, we can simulate everything with our computers. It says nothing about whether we can do it efficiently or not, however. And for the efficiently part, there is the strong Church-Turing thesis that says that every physically realizable computation device can be simulated by a Turing machine with polynomial overhead. And this is essentially saying, because as I just said, that the polynomial time is efficient computation, it basically says that we have an efficient simulation, and it also means that anything that can be solved efficiently with any kind of a model of computation, we can solve efficiently using Turing machines. And this is a claim. The standard Church-Turing thesis is very much believed to be true. Nobody, essentially no researcher studying these things, thinks that the Church-Turing thesis would not be true. But the strong Church-Turing thesis is a different story. And actually, it might well be that it is not true. And it might well be that it's the quantum computers that will show that it is not true. This, however, hasn't been conclusively proven yet, as I'll explain a bit later. So, before we get into talking about what the quantum computers cannot do, let's talk a bit about what classical computers cannot do efficiently. And this should be familiar to computer scientists, and hopefully is familiar also for others of you. It's the P versus NP question. It's $1 million question, literally $1 million question, because there is a prize of $1 million for whoever settles this problem, which is kind of like an awfully small amount of money, to be honest. And it's also our first piece of the alphabet soup we're going to boil today. So we will see lots of very weird abbreviations of complexity classes. You don't need to remember these by heart. I think that what you will learn from today's lecture is that these complexity theorists truly love coming up with completely incomprehensible abbreviations. Sorry about that, but that's how it goes. And the first two of these is P and NP. So the class P is the class of yes-no problems that we can solve in a polynomial time by a classical computer. So in other words, these are the problems we can solve efficiently using a classical problem. The P stands for polynomial. There's a technical detail. These have to be yes-no problems. So these are problems where the answer is always either yes or no. They're not problems where you try to compute some number. That's mostly a technical thing. And I won't go into the details for today because that's a topic of a specific computational complexity course. But for now, you just have to agree that it doesn't matter too much that we limit ourselves to just yes/no questions in here. So an example of a problem in P is, for example, if I have two web pages, A and B, and a question is, can I reach B from A by just clicking the links on the pages? So you give me two arbitrary web pages, and I start from web page A. I see what are the links there, and the question is, can I reach B by just clicking links on the different pages? Is there a path? This is just a matter of if there is a path on this graph. This can be solved in a time which is polynomial with the number of pages in the internet. Or another example is that I'm given a list of numbers. Is there median 42? How do I solve this? Well, I just compute the median and I check if it's 42 or not. But here it's important. It's a yes/no question, the type of a question we are dealing with. And it will be yes/no questions for whole of today's lecture until at the very end, I might say a bit about something else. So then the other set, the NP, it does not stand for not polynomial. It stands for non-deterministic polynomial. I will not go and discuss what on earth is non-deterministic means. It comes from non-deterministic Turing machines. You don't need to worry. Just you do need to remember it's not for not. It's non-deterministic. But the set of NP can be defined as the set of yes/no problems where, if the answer is yes, there exists a polynomial-sized certificate and a polynomial time verifier that, given the problem instance and the certificate, can verify the answer. So it's the set of problems where verifying the yes answer is easy. Verifying the no answer doesn't have to be easy, and it can be very hard. But the yes answer we need to be able to verify easily. It is not known whether P equals NP. That is the $1 million question. In case P equals NP, weird things happen, which I will not go through, but it's generally believed that weird things don't happen, and as a consequence, we do believe that P is not NP. But we can't prove that, and that's the big open question in computer science. I would say this is the biggest open question in computer science. However, clearly, P is a subset of NP. So if a problem can be solved efficiently in polynomial time, then we can obviously easily verify whether its answer is yes. The verification is simply solving the problem. And now let's see some practical examples to get some idea. What does this certificate and verifier mean? In case you have, by the way, studied this before and you've studied NP as something that the non-deterministic Turing machine can do in polynomial time, this definition is equivalent and does not require non-deterministic Turing machines. Why it's equivalent, I leave this as a homework for those who know what I'm talking about. And now let's see the example. So first example, can I visit every Wikipedia page by following links to other Wikipedia pages without visiting any page twice, aka Hamilton's path? Now the n, the size of the input, is the number of Wikipedia pages, and the certificate is just the list of Wikipedia pages in some order, and then the verifier will simply start with the first page, go from the first page to the second page on the list, checks that it's possible that there is a link from the first page to the second page, and then from the second to the third, and so on, and then checks that this list only contains every page exactly once. So that's what the verifier needs to do. It's very simple verifier. It just needs to verify that there is always a link between two consecutive pages on the list, and that no page is there twice. So it's obvious that we can do this efficiently given the original Wikipedia plus this certificate, then this verifier is quite easy. Finding it is a different story, the certificate that is. A classical example that we're given a formula in a propositional logic. So for example, this kind of x1 or x2 or not x3 and not x1 or not x2 or x4. Does there exist a truth assignment to its variables that makes it true? So can we set x1 to something true or false and x2 to true or false and so on, so that this whole formula is true? Here n is the number of variables, and certificate is a truth value assignment for those variables, and the verifier is just some algorithm that checks that if I apply this truth value assignment, I'll actually do have the full formula evaluates to true. That's also very simple. Here, I think it's already like it's an important thing to notice that you might already notice that I haven't said what kind of a certificate you can do to prove that there is no truth value assignment to evaluate it true. So if it's such a formula that there doesn't exist any solutions, so the answer is no. Or if the Wikipedia is such that you cannot visit every page once without visiting some page twice. So again, there is no easy certificate to explain that the answer is no. No answer is potentially much harder to verify than the yes answer. But that was the point of the NP. In NP, the NP is the set of problems where the yes answer is easy to verify. And we don't care how hard the no answer is to verify. Okay, further examples. Given a set of integers, is there a subset of them that sums to a given constant c? Now, n, the size of the input, is the number of the integers times the number of bits for representing them, because here it actually really matters how big the integers are. And the certificate is just the subset of those integers, and the verifier is something that checks that this subset is actually truly a subset and that it sums to C. Not very complicated. You see always that the certificates and verifiers are in most cases very simple. In this case, so this problem, given an integer, is it a prime number or not? Now the input size is the number of bits we need to represent the integer. And this is a kind of like an interesting case, because here the certificate is just the number itself. And the verifier is an algorithm that checks if that number is a prime number or not. So this is actually kind of like interesting case. I'll get to this in a second. But before that, one more example. So we're given an integer. Does it have a prime factor smaller than k? So is there some prime factor that divides it that's smaller than k? Now, again, n is the number of bits needed to represent the integer. And the certificate, this is easy. It's the prime number less than k that divides the input. And the verifier needs to check whether this is actually truly a prime number and whether it actually divides the input. And to check that it's actually truly a prime number is the one problem above. And I'll get back to that. How is this number alone a certificate in a second? But before I get to there, I need to talk a little bit more about reductions, hardness, and completeness. So reduction is the key in doing complexity theory. So a reduction from a problem A to problem B is some algorithm that takes an instance of A, turns it into an instance of B, then takes an answer of this instance of problem B and maps that back as an answer of the original instance of A. So on the drawing on the right, R and R prime are the two parts of the reduction. And then there is some algorithm X that, given an instance of B, can solve it. We don't actually care whether we know about this algorithm X in the reductions. We only care that the reduction is something that can map an instance of the original problem to instance of the other problem, and then map the answer back. And if this reduction algorithm that does the mapping works in polynomial time, then we say that the problem A is no harder than problem B. And why do we say so? Well, we say so because we can solve the problem A if we have this mysterious algorithm X and our reduction, so the functions r and r prime, then we can solve any problem, any instance of problem A by first mapping them into problem B using our mysterious algorithm X to solve that instance and then map the answer back as an answer of A. So these reductions are basically a way to solve problems via solving other problems. So the way to show that this problem is easier or at least no harder than other problem, because if I would know how to solve the other problem, I could solve this problem. And reductions are key because they establish something that's known as the class of hard problems for a class of problems. So a problem is said to be hard if all problems in a class can be reduced to it in polynomial time. And then a problem is complete if it's hard for some class of problems and it is in the class. So you might have heard, or you should have heard actually, problems like NP hard problems. So they are problems that are at least as hard as any problem in the class NP, and NP complete problems, which are the problems that are at least as hard as any problem in NP and themselves are in the class NP. So in other words, the hardest problems in the class NP. And now if we can solve, in case of NP, if we can solve one problem which is NP complete in polynomial time, then we can solve all of them in polynomial time, because all the other problems we can reduce to this problem, all the other NP complete problems can be reduced to this problem that we were able to solve in polynomial time. And so this would be now this mysterious X on the right, and we could solve any other NP complete problem by just mapping the instances of other problems into this problem we can solve it, and then map the result back. And this is a way to basically establish the hardness. So the reductions are the key in order to establish the hardness of problems. And if we can show that some problem is hard for some class, then if we suddenly show or complete for some class, and if we then show that this problem also belongs to another class, then we know that the other class is no harder or is no easier than this class. So then let's get back to these examples of NP problems. So these are the 5 problems I showed you earlier. They all belong in the class NP. I showed you what are the certificates and the verifiers there. This problem, can I visit every Wikipedia page, is known to be NP complete. It's the Hamilton's path. You should know that. Also this one, known as satisfiability problem. In this particular case, it's the free sat. It's also known to be NP complete. Also this problem, given a set of integers, is there a subset of them that sums to a given constant C? So the subset sum problem, known to be NP complete. However, this problem, this integer, is it a prime number? This actually is in P. So this is why my verifier was just an algorithm that checked whether it is actually a prime number, because I can do this in polynomial time. So if I have a problem which is in P, then essentially I don't need a certificate, and my verifier is just the algorithm that solves the problem. And the final question, given an integer, does it have a prime factor smaller than k, is actually a problem that we don't know. It's probably not in P, but also probably not NP complete. So it's definitely in NP, but probably not NP complete. So being able to solve this problem in polynomial time doesn't actually mean that P equals NP. At least we don't have any proof that it would mean that. Okay, soon we might want to have a break, but before that, let's finally see something quantum, right? Okay, I've spent like the first half an hour or so talking about complexity theory, but this is about quantum complexity theory. So by this time, you should be thinking that, okay, what the heck? This guy doesn't know anything about quantum computers. So first, a quantum computational model. So obviously we need a model for quantum computation. In this course, you should have already seen like way to how that, like I've understood you built some quantum algorithms, played with some quantum algorithm simulator, and so on. But if we want to be able to argue about these things, we need some model to model what does a quantum computation mean, so that we can make some proofs about it. I'm not going to go very detailed through this because we're not going to see any technical proofs today. It's just more that so you see what kind of a model we think here when we think about quantum computing. So we say that the problem, which is a yes-no problem, again, we worry only about yes-no problems, and whose input is an n-bit binary string, is computable in quantum polynomial time for some polynomial p, and if one, there exists a classical algorithm that just takes essentially the size plus the polynomial as an input and then produces a description of quantum gates, of polynomial many quantum gates, each of which take at most 3 qubits as an input. As an output, so the classical algorithm produces these descriptions of the quantum gates, and then we can obtain a solution to our original problem with probability at least 2/3 using a simple procedure where we first initialize our input register into the input plus some working space, and then apply these quantum gates to this input register and eventually measure the first qubit of this input register and output whether the first qubit is 1 or 0. So now you see the quantum the polynomial size appears in few places, or polynomial time appears in few places. So first of all, our classical algorithm that outputs the description of the quantum computer needs to run in polynomial time, and it needs to output at most polynomially many quantum gates. So that's where basically the polynomiality comes. Also, our memory can't be more than a polynomial. We can't have more than a polynomial in many zeros here in our register. And then we have the strict limit that the input, the quantum gates can have at most 3 qubits as an input. It doesn't have to be 3, it could be 5. It doesn't really matter, but it has to be fixed, because otherwise, if we allow like arbitrary large inputs and we can use this to encode the computation, essentially, that would be unfair. It's also not very physically realizable. And typically in theory, we stick to 3 qubits, but it's more a matter of convenience. As long as it's some fixed number, it works. And then the very important thing, as you might have already learned in this course, the quantum computers don't give you yes/no answers, they give you maybe answers. So we require that the answer is correct with the probability of at least 2/3. So unlike your classical algorithm, we don't require that the answer is always correct. We just require that the probability of correct answer is high enough. Now, this model here basically has these quantum gates that gets applied one after another. If you've been building quantum circuits, then you could just replace these like gates that are applied one after another with a description of a quantum circuit of fixed size, of polynomial size. That doesn't change anything again. And this weird looking restriction here says that the input, the quantum system must not depend on the exact input. It must only depend on the size of the input. That's why we have this kind of weird description here. Okay, but this is the model of computation. I won't spend any longer on this. But what I do spend is then to worry that, okay, assuming we have a some problem that we can solve in polynomial time using this kind of procedure, what does it give to us? And it does give us the second or the third case in our alphabet soup, the third ingredient, the class BQP. I really don't know who came up with these names. Really don't know. So the class BQB is the problems, the class of the yes-no problems that we can solve in quantum polynomial time. That is, it's the class of those problems that the procedure on the previous slide could solve with could give you the correct answer with probability of at least 2/3. The abbreviation BQB comes from bounded error quantum polynomial time, but really they could consider having a few more letters. Now 2/3 is a rather arbitrary probability. We could change that to something else as long as it's far away from, it must be like clearly above 1/2. Then everything is fine. Why everything is fine then? Well, basically as long as we're clearly above 1/2 success probability, we can always increase our success by just probability by just repeating the computation multiple times and taking the majority answer. And then if we do this oftentimes enough, we are getting more and more confident that the majority answer is the correct answer, and hence the probability increases. And so now this class BQP is the quantum version of P. So this is the set of problems that have efficient quantum algorithms. And thinking that maybe before the break, I'll do a few more things, but at this point, maybe Tommy, if you can set up the poll, whether people want to have a break or do we do this in one go? And you can, yeah, you can answer the poll while I discuss BPP and P and PQB and NP and all that stuff. So at this point, let's get back to the classical model of computation. So our classical algorithm was doing everything. It gave us an exact answer, yes or no. There was no probabilities involved. So I think letting the quantum computers to play with probabilities is a little bit unfair towards our classical computers. So why would they be allowed to give us like probabilistic answers if the classical computers can't? So obviously we can also say that, okay, let's have a classical computer that has an access to some randomness. It can toss a coin, and let's see if that gives us something. So now we have yet another ingredient in our alphabet soup. It's called BPP. So not BQP, but BPP is the bounded error probabilistic polynomial time. Say that fast 5 times in a row. And that's the class of problems that a classical algorithm solves, gives you the correct answer in polynomial time with probability at least 2/3. So this is the exact counterpart to the PQP in the classical world, in that we also allow the classical computer the probabilistic behavior. So it's the direct counterpart. Now, so definitely a break, I would say.
Yes, it seems that actually in this course, well, we have here also probability distribution right now. So Pauli, I think you can decide. We have even between 15 minutes or just 5-minute shorter break.
We'll have a 10-minute break in.
Okay, let's have a 10-minute break.
I will, yeah, but not yet. I will announce the break, but it will last.
Okay, sure.
I'll do a few slides and then we'll have a break, or a slide and we'll have a break. Okay, cool. So now P is part of the BPP. So if we can have the answer with like exactly, we can have it with probability 2/3, obviously. But there can be something which we can have, like some problems we can solve in polynomial time with probability 2/3 that we can solve in polynomial time with certainty. It is possible, but we don't actually know. So we know that P is a subset of BPP, which is a subset of BQP. But we don't know if these containments are proper. So we don't know if there exists a problem in PPP that's not in P. So a problem we can solve efficiently with probability 2/3, but cannot solve efficiently with probability 1. And we don't know if PPP is a strict subset of PQP. So does there exist a problem that a quantum computer can solve efficiently with probability 2/3, but a classical computer cannot? And on that bombshell, we'll have a break of 10 minutes. So my watch is 5 past, which means that we'll continue 1/4 past.
Sounds good. So see you 1/4 past.
It's 1/4 past. So I guess we just continue. And actually, Tommy, are the polls pretty different polls?
Yes.
Yeah, so if you can put the first one.
Okay.
So now to keep you, get you back into the stick thing, soon there will be a poll. Okay, so and in the meantime, we'll continue the discussion here. So we ended before the break on this class PPP, which is the class of classical problems we can do in polynomial time, where the answer is not necessarily exact, but also where the answer is we're answering only with probability 2/3 correctly. So we can have a probability 1/3 to be wrong. Again, with the 2/3 being somewhat arbitrary. As long as it's clearly above 1/2, we are fine. Now, we believe quantum computers can solve in polynomial time problems that classical computers cannot solve in polynomial time. This is to say, we believe that P is a proper subset of PQP, but we don't have a proof. Why we believe it is I think the Shor's algorithm. I'm not sure if you have it so far or will have this course, but the Shor's algorithm is the famous algorithm that shows that you can use a quantum computer to find the integer, the prime number factors of a large integer efficiently in polynomial time, which is a problem which is not known to be in P, as I told you, that was an earlier problem, but which we know we can solve efficiently with quantum computers. However, we don't have a proof that this problem wouldn't be in P, okay? 31 say yes, 31% say no, and 38% say I don't know. Interesting. You can, Tommy, put the next poll. Okay, so we don't have a proof of that, but we believe that the P is a proper subset of PQP. Then we don't know whether they are able to solve NP-complete problems in polynomial time, the quantum computers. Because, as important, the factorization is not known to be NP-complete. So it's a really common misconception that I hear is that the quantum computers would be able to solve NP-complete problems in polynomial time. There really isn't any evidence that they would. Maybe they can. I mean, we don't even know whether P is separate to NP. So it's possible that a classical computer can solve an NP-complete problem in polynomial time. But we don't have any evidence that the quantum computers would actually be able to solve NP-complete problems in polynomial time. Because again, remember, integer factorization is not known to be NP-complete. So if nothing else that you remember from today's lecture, remember at least this: quantum computers are not known to be able to solve NP-hard problems in polynomial time. Okay, so now that the probabilities are different from the previous one, or the distribution is different, either you did listen to me or not, but basically the question was the same. The first question just using English, second question using these weird abbreviations, but clearly answers are different. I don't know whether that's because you've learned, you are saying more no, or actually you're saying way more I don't know than previously. but at least they are different answers for the same question. Interesting. Let me proceed. Yeah, this is the thing. Remember at least this. Not know. All right. You might have heard of Grover's algorithm, in quantum algorithm, which lets us to do a black box optimization in the square root of the search space time, which is actually pretty cool. So we can find a space, we can find from a black box space the optimal solution without having to try out all of them. It's enough to try just the square root of the options, essentially. But that algorithm doesn't change the fact about the NP completeness, because that's essentially, if your problem is NP complete, then with the classical computer or the search space is essentially 2 to the power of n. And if you now can take a square root of that, you get into the 2 to the power of n divided by 2. But that still is exponential. So you don't actually get from exponential to polynomial by just taking a square root. So Grover's algorithm definitely won't be the key for quantum computers to solve NP-hard problems in polynomial time. And actually, Grover's algorithm is asymptotically optimal, meaning that no black box quantum algorithm can do better than square root of the search space, which means that if it so happens that quantum computers actually are able to solve NP-complete problems in polynomial time, they have to be somehow based on the structure of the problem. So they won't work with this magical approach where you just like give them a problem, they don't know anything about it, you just have some kind of a generic quantum optimizer which will take any old problem you throw to it, and it will somehow magically in polynomial time give back the correct solution. No, if they can do this with NP-complete problems, then there has to be an algorithm that somehow takes into account the structure of the problem. And it's not just a black box optimizer. Tommy?
Yeah, so maybe I can actually ask here one question. So yeah, actually tomorrow we will be going. Yeah, so this year we have a slightly different order in the lecture. So I think tomorrow we will go through some of the Grover algorithm and also hopefully the key ideas and the Shor algorithm. Let's see. But basically, Pauli, can you correct me if I'm completely mistaken? But when it comes to the Grover algorithm, so this is kind of like it's more used to argue on that okay, it's possible to do this when you have a black box, that you can say something about the number of function calls or queries, but it's not probably something you would okay, now I will implement the Grover search algorithm, to search things faster. It's more about the making a point about the how many queries you can reduce, but it's not necessarily a practical algorithm. So there is the quantum oracle, particularly, that we have to have in place before we, when we make this algorithm. So just curious.
Yeah, you are probably right, but I have to admit that my experience of implementing quantum algorithms on real quantum computers is so thin that I don't have a very good intuition of what actually will eventually be practical algorithm. But you're probably right. I mean, people, I think, generally assume that Shor will be eventually implementable. But even that, obviously, we're nowhere close to being able to have a practical Shor as of now. But yes, good. So, but in any case, the Grovers, which we will then see soon, is not going to solve your problem either. So to draw fancy circles at this point, where we are is this. So these circles denote the different complexity classes we've seen so far, and they are contained, but the only thing which is properly contained to all of them is the class P. And we don't know whether actually class P is all of this stuff. So we don't even know whether it's a proper subset. I draw it here as a proper subset of them, but I don't actually know for certain whether it is. It might be that P equals NP and P equals PQP, and they all are just one big class of problems. But this is approximately what we assume right now. Now, Tommy, I think we can have the last poll. So then at this point, so there's one more poll, which I will come in a second, but try to answer in the meantime. So we go to something beyond BQP and NP. So is there something beyond? Like so far we've been talking about the efficient computation and then the NP complete thing, which sounds like, oh, these are the hard problems. The question is there something that goes beyond? Is there something even harder, a set of even harder problems? And obviously there is. So there's XP. That is the set of problems that we have a classical algorithm that takes time to the power of n to the power of c. So for some constant c. So exponential time computation. This set contains NP. Why it contains NP? Well, we can simply try every single solution to the problem and see if one of them is the yes, or we can try every single certificate, because the certificate has to be polynomial size. So if you think they are bits, there's only 2 to the power of n to the power of c different certificates. So we can just try every single different certificate and check whether this certificate verifies the answer yes, then the answer is yes. And if none of the certificates verifies the answer yes, then, well, the answer is then no. Also, PQB is part of X because within the exponential amount of time, we can simulate all of these quantum machines all fine, no problems with that. And now 83% of you say that if the space is the only thing that's limited, then the computer can take arbitrarily long before stopping. We'll get to that in a second. 83%. Okay, I'll leave this showing. Good. So then we have that set of problems with limited space. That's called P space. P for polynomial, space for space. So the set of problems with a classical algorithm can solve in a polynomial space. There's no limit on the time complexity. Well, NP is in P space because, well, there's only polynomially sized certificates, so we only need polynomial working space to try out every single certificate. No problem with that. BQP is in P space. That's actually it's a non-trivial. Why can we simulate a quantum computer in polynomial space? But there's something called Feynman's path integral, which I will not go into, which gives you the proof. If you feel that, oh, wow, this is pretty straightforward and easy, contact me. I might have a master's thesis topic for you. Then finally, P space is actually a proper subset of X, because if I'm only given a polynomial amount of space, my computer cannot run unlimited amount of time until it stops, because after exponentially many steps, it has written every single potential configuration in the memory, and then it can have a few different states, after which it has basically tried every possible configuration of the computation. And then it either repeats from the beginning and then it will never stop, or it will have to stop. So 17% of you were correct on the poll, 83% of you were wrong. If you were in the 17%, tap yourself on the shoulder. If you were in the 83%, next time read the bottom of the slide before you answer the poll. Well, any case. So the point is that with limited space, at some point, we've just tried every possible configuration in the space, at which point we either start from the beginning, and if we do start from the beginning, then we will never stop. And if we don't start from the beginning, we have to halt, and that's it. So P space is actually properly contained in the X. And then there's one more, the class PP, which is in the BPP. I said that the probability has to be properly above 1/2. It was set to 2/3. I said it doesn't really matter as long as properly above 1/2. But this is crucial. It has to be some constant amount above 1/2, because if PP, the class PP, is the set of problems where it's enough that it's correct with some probability, which is above 1/2, but it can be exponentially close to 1/2. So, for example, the answer, the yes answer, we might be giving yes answer probability, which is 1/2 plus 1 divided to 2 to the power of n, and then we say on no instances we say yes with the probability which is 1/2 minus 1 divided by 2 to the power of n. And actually the probabilities get so close to each other that we can't really tell them apart. So technically, yes, we have a probability larger than 1/2 to be correct, but in practice, or like technically, yes, but then in the computational point of view, it's so close that actually it lets us to cheat the system. I will not go through the proof how, but you just have to believe me. And it actually is so that with this kind of cheating that we can do, we actually can solve the problems in PQP, so all the quantum problems efficiently using classical, or we can solve all the problems that we can solve in quantum computers efficiently with the classical computer that has this cheating option for the probability. We can obviously solve all the problems in BPP, so the ones where we have to be properly above 1/2 using this kind of cheating option there. And NP, all the NP complete problems can be solved if we allow ourselves to kind of like cheat, to be above 1/2, but kind of like so little that we cannot anymore use this like repetition trick to get ourselves in an arbitrarily good solutions. And well, this algorithm clearly doesn't take more than polynomial space. So this gives us this set of new circles. So the class PP is kind of like a class of stupid problems. Nobody wants to solve those problems, but it's interesting because it's the smallest set, smallest complexity class that is known to contain all PQP and NP and BPP and P. And then PP is contained in P space, and P space is contained in exp. And now, if somebody like some of you is able to prove that PP equals NP, then because of all the containments, the problem turns into this. So if PP equals NP, then we know that PQP has to be a strict subset of NP, because PP contains also PQP. And so our world turns into something like this. And if somebody is able to prove on contrary, or in addition, that PP is PQP, without saying anything about the NP, then we know that NP has to be a proper subset of PQP, so that the quantum computers can solve problems, can solve efficiently all the NP hard problems. So that's why the PP is an interesting problem class, even though it's kind of like cheating, as I say. Right. That is the end of our alphabet soup regarding the complexity classes and that kind of stuff. The main moral of the story, the main point from this part of the lecture is just to remember that, okay, first of all, these kind of things are studied, even though we don't have the quantum computers. And yes, remember, we don't have any reason to believe that quantum computers would be able to solve NP complete problems in polynomial time. So those problems the computer scientists in classical computers have considered hard, they stay hard. But then they might be able to solve some other problems efficiently that the classical computers can't. So the integer factorization is a prime example. And when they can, happens what's known as quantum supremacy. It's kind of like an unfortunate term, if you ask me, especially in the US. So quantum supremacy is not a well-defined term. It refers to this kind of like a point at which point the quantum computers can solve a problem a classical computer would take an intractable amount of time to solve. So we don't really know what the classical computers can do. We don't know whether P equals NP. So we have to basically base our arguments on this quantum supremacy for existing algorithms and our complexity assumptions. So what seems to be the most likely case. Now, this quantum supremacy also kind of like, it's an academic question in the sense that, yes, if we would have a quantum computer that can actually factor a really big integer, that would show definitely clearly a quantum supremacy, so that you can break some cryptography that assumes that integer factoring is hard, and then you have a quantum computer that can do the integer factoring, then clearly we've shown that there's a case where quantum computers are better than classical computers. But that's still far in the future to happen. And so in the meantime, it would be nice to be able to say that, okay, now the quantum computers have surpassed the classical computers, at least something. This something doesn't have to be very interesting or very practical. And typically it isn't, as long as it's something that kind of like is very likely hard for classical computers, and it's something that quantum computers can do. And if we do actually obtain this supremacy, it actually even helps us to kind of like convince that this is truly a quantum machine. So if you can't make much, if somebody just tells that, oh, I have a quantum machine, it might not be exactly trivial to figure out, is this truly a quantum machine or just a fast classical computer or special purpose classical computer? But of course, if the machine can do something that your classical computer cannot, then it's, well, if it's not quantum machine, then it's something even more interesting at that point. So what kind of problem could be? As I said, the integer factorization would be kind of like a clear case, but that's kind of like too far in the future. 2019, Google announced that they've now reached quantum supremacy. Then there was a lot of discussion whether they actually did or did not. But their claim was based on measuring the state of random quantum circuit. So basically, simulating quantum circuits. Quantum computers are presumably pretty good at simulating quantum circuits. That's kind of like what they are. And on the other hand, we know that for this to happen in classical computers, we actually truly need to simulate them in a classical methods, and we think this is hard. So hence Google was using this problem as their example. Another popular problem is so-called boson sampling. This is now used by the University of Science and Technology China and also the company Xanadu that have both made recently claims about quantum supremacy, so that they've been able to do something that would take like trillions of years with classical computers. Boson sampling, basically you sample from a probability distribution of single photon measurements at the output of a linear optical circuit that gets some indistinguishable photons as an input. I don't go to the exact details. What's the key here is that in order to do this sampling, there is some probability that involves computing a permanent of some matrix, and computing the permanent is assumed to be hard in classical words. So permanent is this function, which is a little bit like the determinant, except that you don't have the minus ones put around. So if that equation for the permanent would be the equation for the determinant, you would have this minus 1 to the power of the index of the sigma, I think, there, but we don't have that now. And determinant is easy to compute with classical computers. Permanent is hard to compute. And hence, it's assumed the classical computers, like boson sampling, would be an example of a problem that are hard for classical computers. It's actually hard because there is something called sharp P. or hashtag B if you live in Twitter, sharp B, which is basically the set of problems that ask that how many accepting solutions there are for this problem in NP. So how many acceptable answers, how many yes answers, how many different yes answers there are, how many satisfying assignments, how many Hamilton's paths, how many this, how many that. And this is set of problems which is even harder than NP, but I don't go any further with that. The supremacy tests have some problems. You need to somehow validate the correctness of the answer, but you can't use a classical computer to do that, because the whole point of the supremacy test was that problem has to be something which is very hard to compute with a classical computer. And so if you have a machine that a quantum machine that just spits out random answers, that would be very fast, but that wouldn't be very interesting. So you need to have some way to evaluate whether the quantum machine's answers are actually true without having to compute the true answers at the first place. It's a bit complicated. So typically you simulate something slightly simpler, and then you compute how similar the answer is to the somewhat simpler solution, assuming that if you get a close enough similarity, then you are golden. And then you need to also ensure that the problems are actually hard. So if somebody actually comes up with an efficient algorithm for simulating the permanent, then the boson sampling is not a hard problem for classical computers. And actually in the boson sampling, we need to do the permanent of a Gaussian random matrix, and the hardness is only for binary matrices. So it's not actually given that the Gaussian random matrices are also hard. And it sometimes happens with these quantum supremacy claims that first, like when Google announced that, oh, our algorithm is our quantum machine has now reached quantum supremacy, took a little time, and then some researchers came up with better classical algorithm, and so on. So it's not like a fixed state that one day the quantum computers reach quantum supremacy and that's the end of it. That there can be improvements in classical computers that make them to match the quantum computers. We can't rule this out, and it actually would be nice to have faster classical computers. A few random advanced topics I'd go quite quickly, just show you a bit what's there further. First of all, we have discussed about this set NP, so basically the hard classical problems, so to say, those problems where verifying the correct answer is easy, but finding the correct answer seems to be hard. But we haven't talked about, does there exist a quantum NP? So sets of problems where it would be easy for a quantum computer to verify the correct answer, but perhaps hard for the quantum computers to find them. And well, we can obviously easily build such a set of problems. We say it's a set of those problems where the verifier, it's like NP, but the verifier has to be a quantum algorithm, an efficient quantum algorithm. So an algorithm in PQB. And then we get something known as the quantum Merlin-Arthur. So if we replace the verifier with a probabilistic classical machine, we get something known as Merlin-Arthur. So given a certificate, the verifier has to give the correct answer with probability 2/3. And if it's a quantum, then we get a quantum Merlin-Arthur. So that's the quantum NP, but I won't go any further on that topic, but it's there. But then a completely different take of everything. What if we take the P versus NP as a law of nature? So I've been constantly repeating that we don't know whether P equals NP. We don't have a proof for that. But we have lots of empirical evidence that probably P is not NP, and we could just take this as an axiom. We can say that it's a law of hardness of non-deterministic computation. It's a bit like the laws of the thermodynamics, or no speed is faster than light. I mean, we don't have a mathematical proof that the laws of thermodynamics work. It's just something that we have established experimentally. That they seem to hold. So why not have a similar rule for the P is not NP? And then as we do this, we basically get in a model where any physical model that allows building machines that solve NP complete problems in polynomial time becomes a questionable model. So, for example, time machines, so closed time like curves, if you want to have this fancy speech, they would allow solving P-space problems in polynomial time, so all of NP. So if we assume that NP problems can't be solved in polynomial time, then we can't have time machines. Or vice versa. If you do have time machines, then P must equal NP. And so all the sci-fi where you have time machines, but you can't solve NP hard problems in polynomial time, that's actually unrealistic sci-fi. Stop watching unrealistic sci-fi. That's important. As the cryptography, this might be of interest. Some of you, like, are you money safe? Can we have like a quantum? The quantum computers can factor integers. Cryptography assumes integer factoring is hard. Ergo, does it mean that cryptography is broken? Well, first of all, yes, quantum computers can break the RSA public key cryptography and apparently also elliptic curves. They are not known to be able to break private key cryptography like SAH-512, which is something like your hard disk is usually encrypted, and which is actually something often used for the encryption after the initial key share using public key cryptography. And there are sets of algorithms, for example, lattice-based public key cryptography, which the quantum computers are not known to be able to break. So we've been preparing for this now for many years. And there is a program by the National Institute for Standards and Technology, NIST, in the US to find the next standard public key cryptography algorithms that are quantum proof. There was, I don't know if you noticed, but there was actually recently a case when one of the algorithms that was on this program as a candidate was broken, so it was defeated by a perfectly classical algorithm, just using some fancy math from other fields. So we don't actually have any proof that any of our cryptography is safe against classical computers as such, because we don't have a proof that P is not NP. And if P equals NP, all of our cryptography is gone. So all this is based on assumptions that certain things are hard, and it is possible that those things we think are hard turn out to be easy, even in a classical world. And if all of this lets you into thinking that, oh, right, so what are these quantum computers good for? So I've been studying them, and I will study more of them. But I mean, that guy, he just came telling me a huge amount of weird abbreviations, and then the take-home message was that they can't solve those problems I thought they are able to solve. Well, first of all, they will be good for simulating quantum systems and doing stuff like that. And that's, I think, is the most certain use case for quantum computers, definitely. They will probably also be useful for factoring integers, for whatever reason you want to do that. They might be good for other topics as well, but this is still somewhat open question. They definitely don't seem to be able to solve NP complete problems, as I said. And in lots of the modern day quantum algorithms, there is this problem that they require turning your classical input first into a quantum input, and that is a hard problem. And there was, for example, just recently an article at the Journal of the ACM that shows that essentially all of the quantum machine learning algorithms that have been proposed recently can be implemented with polynomial slowdown using a classical computer. So basically the quantum, the quantum computers don't really bring much anything new into those proposals. So this does not mean that we couldn't be able to come up with other quantum machine learning algorithms. But I think getting from classical input into the quantum input is quite hard, in fact. And that said, because we don't really have practical quantum computers yet, I don't think we have really even started even to dream about what we could do with the quantum computers. So it's really, truly infancy, and it might well be that if and when we start getting them, we start coming up with ways and we start understanding how to use them truly efficiently, maybe solving problems we don't think are problems right now. Like, I don't know, finding bots in Twitter. Oh, second last slide. You might be wondering how many of these complexity classes there actually are. So I showed you a bunch, and there's many more. This is very hard to read, but this is the containment graph of the various complexity classes from the complexity zoo. You can go and check this out, complexityzoo.net. It contains currently 545 different complexity classes, and things that are like hierarchies, like parameterized complexity classes, are considered as one of few. Okay, to sum up, approximately in schedule, quantum computers are not known to be able to solve NP-complete problems efficiently, and most experts think that they will not. They are at least as powerful as standard computers, and most believe that they're actually more powerful, and if they are more powerful, then the strong Church-Turing thesis will be wrong, which is actually a big deal. There's awfully little we can prove in terms of separations between these classes. So very few classes we can actually tell properly apart. That you can say this is a proper subset of this other class. But then actually lots of computational complexity theory has developed tons of proofs to show what types of proofs won't work. That, however, is a story for another day, as they say. And on my part, thank you.
Thank you, Pauli. So, do you have any questions? Well, okay. I think it always takes some time before people are bringing
this alphabet soup is thick.
Yeah. So Pauli, perhaps more like well, your personal view. Like, are you more an optimist or pessimist, or something a realist? Well, how you would call like currently, I think the quantum computing, there are a lot of money flowing in, a lot of studies on different sides of this one. But what's your personal, like? Are you excited or perhaps more concerned about how the future may look like?
I'm very hype averse person, which is to say that I'm actually very afraid of the quantum computing hype, because I do think they're really intriguing things. I'm still waiting for somebody to build an actual practical one, but kind of like I believe I'm not an expert on quantum engineering, but I believe that it's possible to build one, or if it's not, then that would be actually an interesting physical realization as well. But I think it's a little bit similar with the AI hype going on right now, that people think that maybe the quantum computers can solve all the problems in the world very efficiently, probably together with the deep neural network. So I'm waiting for the deep quantum networks, or whatever there comes out. And then when they realize that actually, no, that's not the case, I'm afraid that then all the funding goes away, and then people kind of like get very disappointed and start thinking that, oh no, so this was all like smoke and mirrors and snake oil all the time. While there's been like a good solid research, but then kind of like the pendulum swings to the completely other end, and so no funding goes to the quantum computers anymore, and no funding goes to the AI research anymore, when they finally realize that we can't build self-driving cars using just deep neural networks or something. So that's my take on all of this is basically that I'm very afraid of the hype, not of the hype itself, but of the backslash that I think will happen. Not because the quantum computers are not interesting or anything like that, but because they cannot possibly fulfill all the dreams people have on them. And then on the research point of view, what I find there is very interesting. I think you, Tommy, mentioned that you had tried some of these like quantum inspired classical algorithms, that when people are working on quantum or study these things, they've given them like inspiration on making classical algorithms, which I think is actually quite, I mean, some of them might work, some of them might not work, but it's like an interesting way to get novel classical approaches as well.
Right. Yeah. So this is a fair point, and yeah, I think the hypes are kind of like dangerous in the sense that you described, and I believe also for myself, like well, I'm curious about many things, and this quantum computing is something I'm kind of like interested of, not because I would believe that you know, that it would replace the current technology, but I think that learning about this these algorithms and this all the ideas itself is kind of like interesting. I think you never know what this knowledge may be used later on, including possibly the classical algorithms. And well, time permitting, like next week, I think we still have some the 2 lectures next week. I may talk a little bit on the quantum machine learning for the little that I know about it, and it's yeah, I'm equally, let's say, conservative on the let's say speed ups or practical things to work immediately, but I think we will learn something along the way, and yeah, maybe use some of the some insights from the quantum mechanics or something eventually in classical machine learning. So I think it's in the net result. I think I'm quite optimistic that something will be changed probably, but and maybe this whole thing requires again like new generation in the sense that I don't know what happened like after the Second World War, how much research funding was then going to the classical computers. But basically, I believe that when you give geeks or nerds some new tools, that they will figure out in the long term what's that good for. And maybe we don't know everything yet.
And I have to say, I cannot be entirely sad if everybody has to study Pauli matrices and Pauli exclusion principle. I mean, they have nothing to do with me, but I still find them cool. Yeah, especially Pauli matrices.
Yeah, we should agree. Yeah, next time Pauli could teach Pauli matrices here.
I could teach Pauli matrices. Yeah.
Okay. Does anyone have any questions to Pauli? So yeah, so you will find that there is the quiz of this week, and it includes this few questions from Pauli, and I think you can share the slides, so I will upload to Moodle and to. But that's I think everything. So thank you again, Pauli, for the very nice lecture, interesting lecture. And I think in this course, what I like is that we are learning from let's say different branches. Like okay, and this quantum computing is really, perhaps you can already tell, it combines many things from quantum mechanics to computer science, complexity theory, algorithms, etc. So that's why I find it interesting, and we will continue then actually tomorrow with some of the algorithms. Let's see how far we will get on that route. But that's everything for today, I think, unless Sami or Pirkka have any last announcements. Well, I think the main message is that yes, don't delay this week's exercise until the last minute. So there is some cues on the real quantum computer, so you might be surprised. So that's, I believe, was the main message. Okay, but thank you everyone, and see you tomorrow.
For all for listening. Goodbye.
Bye-bye.